about how we represent sets in diagrams and something called a subset. So let's look at Venn diagrams and subsets. In set theory, we call that the universal set, and we give it the letter U for a name for universal. We're also going to be using these universal sets in order to draw pictures of set relationships called Venn diagrams, and they were named after John Venn. So here's an example of a Venn diagram, and you see the rectangle on the diagram is like the bounds of the universe that we're limiting ourselves to. And so that U there is telling you that anything within this. So as an example, maybe set A might be, well, actually, let's start with U. The universal set U might be 1, 2, 3, 4, and 5. Those might be the numbers in the set U. And maybe the set A would be the odd natural numbers less than 6. So which elements of U are actually in the set A? So we're looking at odd natural numbers less than 6. Well, all of the numbers in U, 1, 2, 3, 4, and 5, are less than 6. The odd ones would be in set A. And so I am looking for 1, 3, and 5. So when we're looking at this diagram, it is basically divided into two regions, and one region is what's outside of A and the other region is what's inside of A. So since the set A consists of 1, 3, and 5, it would be correct to place those elements within the set A. It would be incorrect to also place one of them outside of set A. If in any Venn diagram there is exactly one region that is correct for each unique element. So a 5 should not go out here. Now whatever's not in set A should go out there. So the 2 and the 4, those would have to go outside the circle. Okay. Now we have a name for the region that's outside of the set A. We call it A complement. And the notation for A complement is the set A with a little dash, like a apostrophe up and to the right. And sometimes we call that A prime, or we just say complement of A or A complement. So in this case, in the example that we discussed, where U contained 1, 2, 3, 4, 5, and A was the set containing 1, 3, and 5, then A complement would be the set 2, 4 that contains the elements that are not in A. Now let's define formally what it means to be the complement of a set. So this is going to use that set builder notation that we discussed last time. So let's read through it carefully. When you're reading math, you have to go through it slowly and probably read and reread it a couple of times usually before you kind of get the gist, because it's very dense, because all these symbols represent several words. So for any set A within the universal set U, the complement of A, which is written A with a little prime symbol next to it, is the set of all elements of U that are not elements of A. So this word, when you see not, you know we're talking about a complement. And the way you write this definition in symbols is this: A complement that's not in A, it has to be in the set U. Remember, this elongated E means element of. So X is an element of the universal set U, and simultaneously, X is not an element of the set A. So you will need to be able to read that definition in symbols and recognize that they're talking about a complement because we're talking about elements that are not in A. Now, there may be multiple sets within the universal set. They might overlap or be separate, and one can be contained in. Okay, sorry, we're lagging here. All right, but in the picture on the right, unlike the picture on the left, A and B overlap, but A might not be contained completely within B. In other words, maybe there's an element 5 that is outside of B, but inside of A. That's not possible the way the diagram on the left is drawn. So the way you draw the diagram depends on what your needs are and how the sets are related to each other. Now here's a diagram which emphasizes that A and B in fact have nothing in common. They don't overlap at all. Okay, so in the diagram on the left, we could say that A is contained in the set B. So in set theory language, we say A is a subset of B. That's not indicated by the other two diagrams. So let's talk about subsets, or sets that are contained in other sets. When we have this conversation about subsets, the symbols are going to be very similar to the symbols you use for inequalities. So I just want to remind you, remember how in algebra we use this little symbol here for less than? 3 is less than 5. In other words, 3 is smaller than 5. And we also say that it would be true that 3 is less than or equal to 5. And it would also be true that 5 is less than or equal to 5. This or equal to gives us more flexibility because it's possible that they're equal and it's possible that one is less than the other. In either case, it would be true. All right, so I just want to remind you of this notation because we're going to use something very analogous in our notation for subsets. So this is more general when it has the or equal to, because it can allow for equality or not equality. All right, so now let's talk about the symbols for subsets. A set A is a subset of a set B if every element of A is also an element of B. In symbols, the way we write that is a subset of B. Now notice this subset symbol. Let's talk about where the subset symbol comes from. Remember, this means that A is contained in B. So you could think of this symbol as being an elongated C for contained in. But in the bottom we have a line. Just like in the inequality symbols, this line is indicating it's possible that A is actually equal to B. So either A is contained in and smaller than B, or A is contained in and equal to B. But we just read it as subset. Don't read it as or equal to like we did with the inequality symbols. So this is an example of a type of problem that you might have. You might be asked to fill in the blank with either a subset or not a subset. Right? Whenever we cross through a symbol, it means not. So we have in part A the set containing A, B, and C. And then we have the set containing A, C, and D. And we're being asked to use one of those two symbols. Either it is a subset or it's not a subset. So to be a subset, it has to be completely contained in the other set, meaning each element on the left is also in the set on the right. But we can see here that B is not in the set on the right. So that means that this is not contained in, so that's not a subset. for part B, we have 1, 2, 3 on the left and 1, 2, 3, 4 on the right. 1, 2, 3 is contained in 1, 2, 3, 4 because 1, 2, and 3 are each elements of the set on the right. So we would say subset of. Okay, now suppose that A is a subset of B and B is a subset of A are both true. Then that would mean that the two sets would have to be equal to each other, right? Because each one has all the elements of the other, which was our definition of set equality we learned last time. But what if we wanted to specify that a set is not equal to the larger set? So we call that a proper subset, when the subset is contained in but not equal to. So it's a subset of the original set, but it's not equal to the original set. Then we're going to say that it's a proper subset. And the symbol we use, not surprisingly, is the same symbol as subset, but just without that or equal to line underneath. So sometimes you'll be asked to place either subset, the symbol for a subset, the symbol for proper subset. Uh-oh, having issues again. Let me pause. Okay, looks like we're coming back. Sorry about that, guys. Okay, so sometimes we're asked to decide if we have a subset, a proper subset, or both that could make the statement true. So remember, subset means that it's contained in and possibly equal to the other set. Proper subset means it's contained in but not equal to, so there has to be at least one element of the larger set that's not in the smaller one. All right, so let's look at A. So let's check, is ABC contained in ABCD? So A is in ABCD, B is in ABCD, and C is in ABCD. So definitely we have a subset. That'll work. But isn't it also true that these two sets are not equal to each other? So it would also be true to say that it's a subset. So the answer to part A would be that it would be both. Now for part B, we have 1, 2, 3, 4. These are all in 1, 2, 3, 4 with nothing extra. So it would be true to say that this is a subset, but we could not say it's a proper subset because they are in fact also equal. So the answer to part B is only the subset symbol. Let me know if you have any questions. You can type them into the chat bar. Or if there's anything I need to repeat, especially since we're having some buffering issues today. Okay, so I got to get this little message about John McCain off my screen. Okay. Notice that a proper subset is always a subset, but the converse is not always true. So a subset is not necessarily a proper subset. Okay. So when you're asked if a set is a proper subset of another set, you basically have two conditions to consider. First, are all of the elements of the set in the other set? If yes, then you know it's a subset at least. But if it's not a subset, it definitely can't be a proper subset. You can stop. But if they are elements of the other set, if you know you have a subset, then you ask yourself, are the two sets equal? If yes, then the set is a subset of itself, but not a proper subset. And if no, then it's both a subset and a proper subset. And remember, all of these notes are going to be in the link in your classroom. So not only do you have access to the recording of this lecture, but also the notes as well. All right, try this. Determine whether N is a subset of W, a proper subset of W, both or neither. So does anyone remember what N and W stood for? This is supposed to be, by the way, a boldface N and a boldface W. Let me just emphasize that. This is supposed to be a capital bold N, capital bold W. Remember, these represented they're defined to be very specific sets of numbers. Does anyone remember that could type it into the chat bar which set of numbers N is or which set of numbers W is? I'll give you a clue. It's not the rational numbers. That was represented with a Q. Very good. Natural and whole numbers. Excellent. So remember, the natural numbers referred to the set that you can see. 1, 2, 3, and so on. Things you can count. The whole numbers, we just threw in 0. Okay? So we're being asked to determine is if the natural numbers is a subset of the whole numbers, or if the natural numbers is a proper subset of the whole numbers, or both, or neither. Okay, what do you guys think? First, let's start with the process. So the first thing you ask yourself is, are the natural numbers all entirely contained within the whole numbers? In other words, is every natural number also a whole number? So that would mean that the naturals are a subset of the wholes. Is that true? Good, Kelsey. Yeah, you're right. The naturals are within the wholes. 1 is in there, 2 is in there, 3 is in there, and so on. Okay, now, are they equal to each other? Do the natural numbers actually equal the whole numbers? Would that be true? Nope, because 0, good. That's right, because 0 is in the whole numbers, but it's not in the natural numbers, so they're not equal. So what we can conclude is that it would also be true to say it's a proper subset. It's both a subset because it's contained in, and it's a proper subset because it's contained in but not equal to. So the answer would be both. Okay. All right, so now we're going to talk about, now that we've defined what subsets and proper subsets are, we're going to talk about how to count the number of subsets of a given set. And one method of counting subsets, what we're looking to do is to come up with an organized way of counting how many subsets there are, and doing that without overcounting, counting anything twice, or undercounting. So what we're going to do is we're eventually going to work our way up to a formula you can use to figure out the number of subsets of any set. But in order to get to that point, we're going to actually start by listing out the subsets of a given set. We're going to start with a very small set that only has 2 elements. Excuse me. The set containing A and B. And we're going to use a method of organizing our work called a tree diagram. Tree diagrams will be useful in a couple of contexts, so it's good to get comfortable reading them and understanding what they are. All right, so in this case, what I've done is I'm organizing my work into answering 2 questions. Whenever there's a subset, it's either going to be the case that A is in the subset or it's not. And it's going to be the case that either B is in the subset or it's not. So what I'm going to do is I'm going to draw a picture. You can think of this as a tree that starts at a point and branches out. And the first branches here represent the answer to the question, is A in the subset? There's only 2 possible possibilities, 2 paths that can happen. Either yes, it is, or no, it's not. And then the same thing for is B in the subset. Regardless of whether A was in the subset or not, we have 2 possibilities. B could be in the subset or not be in the subset. So we end up branching out, doubling the number of branches here when we answer the second question, because in each case we need to follow up. So you see what happens? We get, for example, this top branch here represents the situation that both A and B are in the subset. So that would be the case where we have A and B in our subset. Whereas the next branch, which I'll highlight in green here, in this branch represents the case where A is in the subset but B is not in the subset. And I think a lot of times, so that would be the subset just containing A. I think a lot of times people have trouble reading this because they try to read this direction. And what you want to do is look at the end of the branch and kind of go backwards. And then there's only one path you can follow. And then it'll be more clear that we're talking about a yes and a no. Let's look at this third branch here. So following backward along the branch, you see that it hits yes and no. And so this is a situation where A is not in the subset, but B is. And then this last branch, following backwards, it hits no and no. And so that would be that very special set we talked about last time that has no elements in it whatsoever. That was called the empty set. You could also represent it with a circle with a line through it. Remember, where this circle comes from is Venn diagrams, because we represent sets with circles, and we have the line through it to show you there's nothing in the circle. Okay. So anyway, we have figured out that there are, this covers all the different possible scenarios. So there are exactly 4 subsets of this particular set. Okay, let's try a different problem. Here we're asked to list all the proper subsets of the set 3, 6, 9. This is a 3-element set. It's a little bit bigger, so it's going to mean a larger tree diagram to list out all of our subsets. And since it's proper, we're just going to leave off the one that's equal to the original set. So you have 3 questions to ask yourself. In this case, is the number 3 in the subset, yes or no? The number 6 in the subset, yes or no? The number 9 in the subset, yes or no? You start out with one question and you work your way up. So either 3 is or is not in the subset. There are only 2 possibilities. But then regardless of whether 3 was or was not in the subset, we still have to decide, is 6 in the subset or not in the subset? So we've, again, doubled the number of branches. We went from having 2 branches for the first question to 4 for the second. But then regardless of which branch we're on, no matter what has been decided about the 3 or the 6 being in the subset, we still have to decide if 9 is. So we have 4 different branches already, and we're going to double the number of branches again. So you actually end up with 8 different branches this time, because there were 3 elements this time instead of 2, like in the last slide. Okay, so again, one of the things you have to get used to is reading the tree diagram and knowing what each branch represents. I'm going to start at the top again. So the top branch represents 3, 6, 9. Why? Because if you go backwards, you can see that we're tracking along. There's only one path to take. If you start at the end of a branch and go backwards to the beginning, you see it hits yes, yes, yes. So 3, 6, and 9 are all in the subset. Now we're not going to include that in our list because it's not a proper subset, but it does show up on our diagram because all subsets show up on our diagram. Now the next branch represents 3, 6. Why? Because if you go to the end of the branch and you track backwards, you see that you get a yes for 3 and a yes for 6, but a no on 9. So only 3 and 6 are in the subset. Okay, take a moment and see if you can figure out what each one of these branches represents. I'm just going to pause so you can kind of maybe jot it down on your paper at home, and we'll see if you get it right. Test yourself, see if your instincts are right. Okay, so hopefully you had a chance to jot down what you think each branch represents. The next branch represents 3 and 9 because it's a yes, no, yes branch. The next branch represents just a 3 because it's yes, no, no. The next branch represents 6 and 9 because it's no, yes, yes. Then we have just 6 because it's no, yes, no. Then we have just 9, no, no, yes. And finally, we have the empty set. So when we're asked to list all the proper subsets, then we've used this method of systematically listing them out, all the subsets, but we only want the proper subsets. So here are our proper subsets. Okay, now if on my math lab you had to list those out, you might have to put commas in between. So it gets confusing because you have the commas inside the sets separating the elements and the commas outside the sets separating the sets. You have to have both. So be careful there. Okay. All right, so we have 8 subsets, but we have 7 proper subsets. Okay. So try for a moment to construct at home on a piece of paper a tree diagram for all the subsets of this set, S equals A, B, C, D. Okay, I'm going to get you started by reminding you that you're going to basically have to answer 4 questions, 1 question for each of the elements. Is A an element of the subset? Let me call this, let's give the subset a name. Let's call it T. Is A an element of T? Is B an element? Oh, hold on one second. I'm getting sloppy here. Is B an element of the subset T? Is C an element of the subset T? Is D an element of the subset T? All right, so the first, it's going to take up some pretty big space, because remember, each time it doubles the number of branches, every element that you add on there. But the first branches will be yes and no, and then you're going to have to branch off from there, and then branch off from there, and so on. So try jotting that down on your paper. Give yourself space, because it is going to spread out. Yes, Kelsey. Kelsey just asked a good question. She asked, is an empty set considered a proper subset? And the answer is yes. The only subset that is not a proper subset is the set itself. So the empty set is considered a proper subset. And the empty set is a subset of every set. So you're always going to throw that one in there. Okay, so hopefully you have either all or part of this tree diagram drawn out on your paper. Remember, if you can draw it out, you're going to understand it on a deeper level than if you just see me do it. So it's important to try these things at home. I always tell everybody, you know, I can watch someone run a marathon, but that doesn't mean I can do it, right? So I got to actually get out there and do some exercise if I'm going to have any chance of success with that. Okay, so here is a nice, neat version. Yours is probably going to look a little messier, but this is the general idea, and hopefully yours looks similar. So let's talk about what each of the branches represents. So as long as you have your yeses on top and your no's on the bottom in each pairing, your subsets that you list should be exactly the same as mine. So first you should have the first branch will be all yeses, so that means all of the elements are in the subset. The next branch is 3 yeses and a no, so A, B, and C are in the subset. The next branch is 2 yeses, a no, and a yes, so A, B, and D are in the subset. The next branch is yes, yes, no, no, so only A and B. The next branch is yes, no, yes, yes, so A, C, and D. And then we have yes, no, so just A and C. Then we have yes, no, no, yes, so only the first and last, A and D, are in there. And then yes, no, 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 so only A. Okay, how are we doing so far? Did you get all of those subsets so far? So those are all the ones you'll notice where we had a yes on the A. So all of these contain A. Now down here, where all these branches that are left, no is the answer for A. So you're going to see that none of these have A's in them. So we have the no, yes, 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 so B, C, D. We have no, yes, yes, no, so just B and C. We have no, yes, no, yes, so that's going to be B and D. And then we have no, yes, no, no, so that's going to be B. We have no, no, yes, yes, so that's C and D. No, no, yes, no, so that's just C. No, 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 yes, so that's D, and then all no's is the empty set. So here is a list of all the subsets of a 4-element set. So we did a 2-element set and we got 4 subsets. We did a 3-element set and we got 8 subsets. And now here we have a 4-element set and we got 16 subsets. So notice that each element doubled the number of branches in the diagram. So we have 2 times 2 times 2 times 2 is 16, or in other words, 2 to the 4th power. So it's not a coincidence that we're raising 2 to the 4th power and we have 4 elements in the set. Because again, each element causes us to double the number of branches. If you're asked to list all the elements, all the subsets of a set, you need to make this tree diagram. But as we've observed here, there's a pattern which doesn't depend on what the elements actually are, that tells us how many subsets there are of a certain size set. The formula is that the number of subsets of a set with n elements is always 2 to the n power. Now that's subsets, but if we wanted to count the proper subsets, we've overcounted by 1, right, the set itself. So the number of proper subsets, we would take 2 to the n power and subtract 1 from it. So you have two formulas here that you're going to need to remember. 2 to the n is the number of subsets of an n element set. 2 to the n minus 1 is the number of proper subsets of an n element set. Okay, don't be afraid to interrupt, say something in the chat if you have a question or need me to repeat anything. Luckily, it looks like mysterious problems we were having has gone away, so we're not having our streaming issues anymore. Yay. Hope I didn't jinx us. Let's see. Okay. All right, so if I asked you to find the number of subsets and the number of proper subsets of the set containing Mathy, M-A-T-H-Y, the only thing, we're not being asked to actually list the subsets, we're only being asked how many of them there are. So the only thing you would need to do is to count the number of elements. So let's see, we have 1, 2, 3, 4, 5. We have 5 elements. Remember, each element doubles the number of branches if we were to actually draw out a tree diagram of the subsets. But we don't need to do that because we only need to know how many. So how many subsets are there? We're going to use 2 to the n, where n is 5. So we're going to have 2 to the 5th power. What's 2 times 2 times 2 times 2 times 2 going to be? That's going to be 32. Okay, so that would be a big tree diagram, right? We'd have 32 branches on that sucker. And then proper subsets, all we have to do is subtract. Very good, you got 32, good job. All we have to do is subtract 1 from it. So we have 2 to the 5th minus 1 is 32 minus 1, which is 31. 1 less than the number of subsets. I wrote this out just so you could see me use the formula, but once you find the number of subsets, you just subtract 1 to get the number of proper subsets. That's supposed to be a U there. Okay. All right, good job, guys. I can see that you're keeping up here. All right, so here's a question from my math lab. It says, Anne, Bo, Carlos, Dean, Ed, and Felicia plan to meet at the hospitality suite after the CEO makes his speech at the sales meeting. Denoting these 6 people by A, B, C, D, E, and F, list all the possible subsets of this group in which 3 people show up. Okay, so this problem is a little bit different than the other problems. In the other problems, they asked us to list all of the subsets. So the most efficient way was to make a tree diagram. But in this case, they're not asking us for all. They're only asking us for subsets of size 3. So you don't actually have to make the tree diagram. You could, but notice that there are 1, 2, 3, 4, 5, 6 people in this set, which means 2 to the 6 subsets, which is 64 subsets, which is a lot of branches. So, and you'd have to eliminate most of the branches because we're only looking for the 3 element subsets. So instead, we're going to use a different type of systematic listing that'll just be less work. And it's also a type of systematic listing that will come in handy later on in the semester when we're doing our counting methods section. So it will be useful to you. All right, so the idea here is to just list all of the subsets that contain the A's, then the B's, then the C's, but never go backwards in the alphabet so you don't accidentally repeat anything. Here's what I mean. So you're going to first do all the 3-element subsets that have an A in it. You're going to do the ones that have an AB, the ones that have AC but no B, the ones that have AD but no B and C, and the ones that have the A and E but not B, C, or D, and the ones that have an AF. So, and then, and I think I'm going to do this by hand so you can see what I'm talking about. So if we're constructing 3-element subsets that have A in it, we could have A, B, and C. We could have A, B, and D. We could have A, B, and E. And we could have A, B, and F. Next, okay, so I've run out of elements that could go with the A and the B. Next, I'm going to list the ACs, but notice I'm not going to go ACB, for example, because ABC is the same 3 people as ACB. You never go backwards in the alphabet, only forward. So instead, you would start with AC and then go to the next letter D, and then ACE, and then ACF. So those would be all the ones that have the A and the C in them, and that we haven't already listed. And then we would do the AD. Again, we won't go back to B or C because we've already listed those. So we would say A and D could go with E, or A and D could go with F, and we've run out of possible letters, as you know, as we can't go backwards in the alphabet, and repeat. So now we're going to go AE. All right, well, we could have AEF, but there's nothing left after that, so we're done. We could try A with F, but since we can't go backwards in the alphabet and there's no G, there's nothing that would be going there. Okay, so the key here is we're not done yet because that's just this subsets of 3 that have A in them, and we're going to move on to the B's in a minute. But I just want to emphasize that we're just systematically listing out the possibilities and ensuring we don't repeat anything by going always forward in the alphabet. I'm going to erase this and put the typed version up there. Okay, we're going to do the same thing with the B's and the C's. So we are going to do B, C. We're going to do the ones that have a B and a D. We're going to do the ones that have a B and an E, and the ones that have a B and an F. And we're going to stay in alphabetical order, so we never go backwards, so we'll never have another A. We've already listed all the ones with A's in them anyway. So we're going to do B, C, D, B, C, E, B, C, F, and there's nothing after that. And we're going to go B, D, E, B, D, F. There is no B, D, G, so we stop. And we can do B, E, F, but there's no letter after that, so we stop. And then it's not possible to get a B, F something because there's no letter after F, so we don't do that one. Okay, so now again, I'm going to erase that, and I'm going to put, well, not yet. And then the C's, never going backwards in the alphabet. So we're going to have some with CD, some with CE, and actually none with CF, but I'm going to write it just to be organized. All right, so we could have CDE, CDF, and then we run out. And then we have CEF, and nothing after that, and then there's none with CF something. All right, so I have listed out all the A's, B's, and C's. What about D's? So do we have any where we could have DE or DF? So DE, we could have DEF, but again, the F doesn't work. And then what about E's. Well, we could have an EF, but then there's nothing to go after the F, so that's not going to work. So now we have a complete list of all the 3-element subsets, and I know that I haven't missed anything because I covered all the letters, and I didn't hit any of them twice, so I didn't overcount. Okay, so this is what it looks like typed up a little more neatly. All right, so that is a systematic listing approach that we're going to use again later in the counting methods chapter. This is how it appears in my math lab. It's a multiple choice question, and they have all the 3-element subsets that we just showed on the previous slide. And that's all that we're going to do for today. I just want to remind you that you should be registered in my math lab at this point. Remember, there is a 2-week free access code, or free access link. When you go into my math lab, make sure to follow the link in D2L if you haven't done it already to go to my math lab. It just says my math lab homework, and you're going to want to work on sections 1.1 and 1.2 at this point. You will notice that the deadlines are posted in my math lab, and several assignments are listed as due at the same time, if I recall correctly. And if that's the case, just make sure that you're pacing yourself appropriately. You can submit late, but you don't want to get bogged down and behind where you're not ready for the test, because if you submit the homework late, you lose points, first of all, and there's no reason not to get 100% on homework, because you can get help with it and you can work it multiple times. So you want to make sure and score as high as possible on the homework, so that way you have a little wiggle room on the tests. Feel free to send me your Ask My Instructor questions too. Remember, in my math lab there's an Ask My Instructor button in the Resources tab, and I love to receive those questions. I've received a couple already. I'm happy to see that, and don't be shy about sending those. I will be posting the link to this live chat, recorded version of this live chat, within the next 24 hours. The reason I say that is because it takes time for YouTube to make it available. But in any case, I will also, in the same place, link where you can see the notes and the video link. You'll also see that I'll post solutions to Ask My Instructor questions there, so everybody can see them.